Welcome today to the third of the Faraday Battery Challenge webinar series that's been running throughout July. I'm Ian Ellerington, Head of Technology Transfer at Faraday Institution, and I'm going to be hosting you today. We're live streaming to YouTube, so you or your colleagues can watch this back at any time. You can use the same link. After today's webinar, you'll receive an email with access to the slides and other relevant materials. Please stick around though, because the interactive session at the end has questions and answers, and so we're really keen to make sure that we answer as many questions as we can live. Today's session will take the format of a 20-minute presentation by Paul Shearing from UCL. We'll then open you up to discussions and questions from the attendees. Please post any questions that you have in the YouTube chat. Your chat host today is Nicoletta Piperidou from KTN. And she's going to ensure that questions are captured and passed over to me, ready for the Q&A session, so you can enter questions at any time. Please be mindful that the audio contains a wide range of backgrounds and knowledge levels. There aren't any stupid questions, there aren't any questions that are too simple, and the plan is we try to catch out Professor Paul with something that he doesn't know the answer to. Following today's webinar, there's going to be an opportunity for you to have a call with either Paul or myself. When you registered for the event, you had an option to opt into the online networking platform to book a meeting with one of us. You should have received an email explaining how to do this, and we'll additionally post a link on screen at the end of the webinar. This will allow us to register. If you have any questions on this, contact Natasha Sim from KTN. This first slide explains the Faraday Battery Challenge. So before we begin the formal presentation, I'm going to introduce that and Faraday Institution and where the research fits in context for anyone that isn't familiar with it. So the Faraday Battery Challenge has three strands of activity, moving along from basic science and the applied science in Faraday Institution through the technology readiness levels to innovation projects run as fairly traditional Innovate UK. And then the UK Battery Industrialisation Centre is a facility that's available to test out new technologies in a pilot production level environment. And that's going to be coming on stream over the coming months. The facility is almost complete in its building. So they've done a pretty good job getting it ready to be used by both the research projects and UK business who have got battery innovations. If we can just move on to the next slide. The Faraday Institution Lithium-sulfur project is one of the research projects. The research projects are split into two areas. There's research on current lithium-ion battery technology, which is about understanding its life, understanding how it degrades, modelling it into systems, and then maybe improving the way that they're built and the way that they're manufactured. And then the second set of projects are our next generation battery chemistries, which will include solid state, sodium ion, and lithium sulfur, and then maybe some additional technologies for emerging markets. And then these are supported by activity on recycling, reuse, building infrastructure, and building the research characterization ability, with some additional projects focused on short-term industry needs and some extra work alongside that on training PhDs. Do you want to move on to the next slide, Paul? So without any further ado, I want to move on to introduce Professor Paul Shearing from the Department of Chemical Engineering at UCL. Paul's the principal investigator for the Faraday Institution's Lifestyle projects, but he has broad research interests across electrochemical engineering. He studies design of electrochemical processes in devices from fuel cells, batteries, and electrochemical reactors. He holds the Royal Academy Chair of Emerging Battery Technologies at UCL, and he's our principal investigator, as well as chairing the Diversity and Training Panel for Faraday Institution. So over to you, Paul, for the introduction to lithium-sulfur.
Thanks very much, Ian. Thanks everyone for joining today. It's great to have the opportunity to present some aspects of lithium-sulfur technology and also of the Lifestyle program, which Ian's just mentioned. So over the next 20 minutes or so, we'll try and give an overview of what we see as some of the challenges and opportunities in lithium-sulfur technology, and give an introduction to the Lifestyle program. And of course, we're going to make sure there's plenty of time at the end to try and address all of the questions that you might have. So do please keep those questions coming in throughout the presentation and indeed through the Q&A, and we'll try and answer as many of those as we can. And as Ian's already mentioned, this is just sort of the start really today of the engagement with the audience. If people want to follow up, do please feel free to reach out to us. And as Ian has mentioned, there is, we're happy to schedule follow-on calls to discuss specifics in more detail. So I think that most people will be familiar with a slide that takes something of this format, but clearly energy storage is a grand challenge of our time. And at the moment, particularly in the automotive sector, that is being met predominantly by lithium-ion battery technologies. And here are some headline targets which were developed by the UK's Automotive Council around about 2016, 2017, for what they felt was the current state of the art, a range of metrics and cost, power density, safety, and so on, and some targets in order to accelerate and make more widespread the adoption of energy storage within the automotive sector. And I think that what you can see from this slide is that the lithium-ion battery technology is very mature and actually very impressive in terms of its ability to meet a very broad range of the criteria that are outlined. It has impressive energy and power density, the costs are always decreasing. Safety, although occasionally we see some hysteria in the press when a lithium-ion battery catches fire, it's actually a very safe technology. We estimate that lithium-ion battery failures are perhaps as low as 1 in 40 million. It's a reasonably predictable technology that is quite durable. It operates over a reasonable temperature range, and that's why it's been so successful. But I think as we look to expand the role of energy storage across a range of applications, not just automotive, but also grid-scale energy storage, consumer electronics, medical and implant applications, and perhaps of particular relevance to lithium-sulfur technology applications in the aerospace sector, there will be a need for competitive technologies to try and improve upon one or more of the metrics that are presented here. If we briefly consider the development timeline of lithium-ion, it was in the late 1970s that John Goodenough discovered the lithium cobalt oxide chemistry at Oxford, and obviously the long overdue award of the Nobel Prize in 2019 was the recognition for the contributions that he and others have made to the development of this really remarkable industry. It took a little bit more than 10 years for Sony to commercialize the first lithium-ion batteries, and they were for applications in consumer electronics. And it took perhaps another 15 to 20 years in order to reach what would be described as the plateau of productivity for the technology and the era of the gigafactory. So actually, lithium-ion batteries are a mature technology, but the development timeline of the battery has been relatively protracted. It's taken quite a long time to get things out of the university research lab into technical application, and then to broaden the scope of that technical application to the position that we find ourselves today, where lithium-ion batteries are really a cornerstone of modern life, powering the laptops and mobile phones that we're using to connect today, and maybe powering your electric vehicle, and one day hopefully contributing to those other sectors in grid-scale energy storage, air and space, medical implants, and so on. If we look to the financial press, there is a message that we think is interesting, but one that we would certainly like to challenge. This is from January 2018, when the FT said today's lithium-ion batteries have barely changed since being introduced by Sony more than a quarter of a century ago. And I think it's an interesting perspective. I think certainly we can trace the ancestry of the current state-of-the-art lithium-ion battery back to those early commercialized batteries that Sony introduced for camcorders and Discmans in the early 1990s. But clearly underpinning the technology that we have driving our electric vehicles today is a huge amount of research and development that gives the high performance devices that we've become reliant upon. A second comment which comes from Deloitte is that at present there appear to be no battery technologies on the horizon that have evolved sufficiently to be tested and factored into supply chains to displace lithium-ion. And again, it's an interesting perspective, but one again that we'd like to challenge, because we think that across those different metrics in cost, energy and power density, safety, operating temperatures, there's actually some very exciting opportunities for battery chemistries beyond lithium-ion to begin to address some of those critical challenges. And that's something that we very consciously set out to do within the Faraday Institution Lifestyle Programme, which is the Lithium-sulfur Technology Accelerator. So when we consider these metrics in cost, energy density, power density, safety, and so on, we also have to bear in mind that in competing with the lithium-ion battery ecosystem, we have to make these technologies mass manufacturable, recyclable, highly durable, and we also need to consider the security, sustainability, and ethics of the supply chain. And I think that if we just take those four headline targets of cost, energy, power density, and safety, we can conceive of next generation energy storage systems that will begin to provide competitive technologies to think about displacing lithium-ion. I think from the context of a lithium-sulfur webinar that we're going to be discussing today, there are particularly compelling benefits around cost. There are particularly compelling benefits around the gravimetric energy density, the energy density per unit weight, and also potentially around safety, particularly when we think about the shipment of large quantities of lithium-sulfur batteries. So, as I said, we'd like to challenge those statements from the financial press, and through the Lithium-sulfur Technology Accelerator Programme and other areas of the Faraday Institution and Faraday Battery Challenge ecosystem, I think that the UK is very well placed to begin to redress some of those comments. So let's start with an introduction to lithium-sulfur batteries from a sort of headline perspective. Lithium-ion cells, whilst they're a wonderful chemistry, have an inherent limit in terms of their energy and power density. And I think that whilst there's been a huge improvement in their performance over the past nearly 4 decades, we're reaching limiting returns in terms of how much further the battery technology can be developed. There are a range of possibilities to displace lithium-ion batteries. Ian mentioned some of them: sodium-ion batteries, solid-state batteries, maybe even more speculative technologies like magnesium or lithium-air batteries. But of the portfolio of next-generation batteries, we think that lithium-sulfur is comparably mature and has possibilities to address some of those critical issues, particularly around cost and gravimetric energy density. The lithium-sulfur cell also benefits from having a benign environmental impact. When you think about a bulk commodity chemical, sulfur is ubiquitous and it's very, very cheap and relatively benign in terms of its environmental impact. And I mentioned that particularly when we consider the shipment of large quantities of lithium-ion batteries, which has been known to cause some challenges, there are some improved safety aspects of lithium-sulfur cells, particularly because we can ship these cells at 0% state of charge, which makes them inherently much safer technology. The spider graph that you can see on the right-hand side is something that we've taken from our recent Faraday Institution Insights paper, and I would encourage all of you to please take a look at that and come back to us with any questions. We've tried to set out what we consider to be the current state of the art in lithium-sulfur technologies, how it compares with current generations of lithium-ion batteries, but also to explore what the future opportunities are. And as I mentioned, particular targets around gravimetric energy density, cost, and the supply chain for lithium-sulfur, we think make it a very compelling technology. At the start of today's webinar, you were asked if you would fill out a Mentimeter poll. And the question of that Mentimeter poll was asking you to consider the relative costs of nickel as a constituent of a lithium-ion battery cathode compared with sulfur as the primary constituent of a lithium-sulfur battery. And I'm just going to flick over to the results now to see what that looks like. So it's just loading the results of the Mentimeter poll. We can see that of the respondents, we had one person reply that sulfur is about the same price as nickel. We had 4 people reply that sulfur is more than 1,000 times cheaper than nickel. And the majority of respondents got it right, so congratulations. Sulfur is, on today's market prices, about 125 times cheaper than nickel. And so you can see that's why we consider it to be a compelling technology when we consider the current and projected cost, and something that we absolutely want to capitalize on in the development of lithium-sulfur technology. So some of these opportunities we've already discussed. Lithium-sulfur is inherently a high energy density per unit weight. It operates over a very wide temperature window. We can ship at 0% state of charge. The materials are low cost. And from a UK perspective, we think that there's a really exciting critical mass both in academia and industry. And as part of the overall Faraday Battery Challenge ecosystem, we hope that we can develop this technology and address in particular some early market opportunities, one of which is highlighted on the picture there. You can see that obviously with those characteristics of lightweight and wide temperature windows, naturally some of those early market opportunities will be in the aerospace sector. And we're very interested in pursuing perhaps smaller scale opportunities for niche market applications, which we hope will then provide some catalytic activity to inspire and develop an entire industry. But naturally, lithium-sulfur is not a technology without challenges. In the current status, we would suggest that there are challenges with the energy density per unit volume. We'd like to make improvements to the power density, to the cycle life. There are some fundamental challenges with the constituent materials and their operation in the cell. First and foremost, sulfur is a well-known insulator. So actually making an electrode out of a relatively insulating material is challenging. And part of this strategy within the LiSTAR program is to think about new materials and materials engineering approaches to address some of these fundamental challenges with lithium-sulfur. Moreover, as we cycle lithium-sulfur batteries, we can lose inventory from our electrodes. There are large volume changes that happen during cycling. And so from a research perspective, we see that there is plenty to get our teeth stuck into, and that's obviously what we're trying to do in the context of the LiSTAR program. But just bear in mind that we are competing with a very mature technology in lithium-ion battery, and we would identify early market opportunities over the next few years to the next decade as ones that can already leverage some of those intrinsic benefits of high gravimetric energy density and the wide temperature window. So if we think about the sort of fundamental differences between how a lithium-ion battery works and how a lithium-sulfur battery works, and there are some really quite substantial differences. A lithium-ion battery, if you take it to pieces, is 2 porous solid materials with an electrolyte flooding the empty spaces between the electrodes. And as we charge and discharge the battery, the lithium ions shuttle backwards and forwards, but the materials largely stay the same. The graphite negative electrode in the lithium-ion battery acts as a host for those lithium ions, but actually from one cycle to the next, as it accepts and then releases those lithium ions, there's not a huge physical change to the graphite electrode. By contrast, within the lithium-sulfur system, as the sulfur begins to react with lithium during those charge and discharge reactions, it actually becomes soluble. So we get a transition from a solid electrode into active materials that are soluble within the electrolytes. And that is key to some of the challenges, but also some of the opportunities within lithium-sulfur. Because the active materials are transitioning between the solid phase and the liquid phase, it gives rise to some of the wide temperature window characteristics of lithium-sulfur batteries. But by contrast, because we have that volume change and that phase change, there are some challenges both from a materials perspective and from an engineering perspective in terms of how we construct the cell. This is the only slide that I've got in the presentation that has a lot of graphs on it, so bear with me while I try and talk through these. The goal to try and improve the specific energy, both per unit volume and per unit mass, has a number of underpinning requirements in order to achieve the targets of 500 watt-hours per kilogram and above. We can see that those fundamental targets can then be translated to materials performance criteria, which includes engineering cells which have enough sulfur in them, making sure that we utilize that sulfur effectively, minimizing the ratio between the amount of solid material and the amount of liquid material that we have within the cell, and also making sure that we're properly balancing the negative and the positive electrode materials. And so there was a recent paper which was published by the Texas A&M group, who have done a lot of thought leadership in the area, where they were targeting the 5 5s for high energy lithium sulfur cells. And this gives us a really ambitious target to try and develop both electrodes, electrolytes, and indeed whole battery systems to be able to begin to tackle and develop lithium sulfur batteries with really enhanced watt hours per kilogram in order to become a challenger to the incumbent lithium-ion battery technology. The graphs that you can see there is part of some thought leadership that we've done in the LISTAR consortium, and it will shortly form a roadmap paper which delves into a lot of technical detail about our vision for developing lithium-sulfur technology. Alongside the much shorter Faraday Institution Insight, I would encourage you all to take a look at that, and do please come back to us with any questions, whether they are in respect of the economics of the process or whether in respect of the technology targets of the lithium-sulfur battery program. We have tried to articulate and provide a forum for discussion of what we see as the roadmap for the development of lithium-sulfur batteries. So I've talked about cost, and we can see from our webinar poll that we have a huge reduction in terms of the active materials cost, but how does the overall cost compare to lithium-ion batteries today? Well, first of all, please bear in mind that because of the enormous economies of scale within the lithium-ion battery industry, we have our work cut out to develop a cost-competitive technology. And if you can see, today's lithium-ion chemistries come in at about $100 per kilowatt hour. The baseline figure for lithium-sulfur batteries might be closer to 200 pounds, per kilowatt hour. But as we can see that rainbow color of bars on our graph there, as we begin to chip away at those targets in reducing the excess of materials, in reducing the intrinsic cost of manufacture and the intrinsic cost of the materials that we're using, as well as utilizing the performance of those materials to the greatest possible degree, we can see that we can translate all of those fundamental improvements to a projected substantial improvement in terms of the overall systems cost, where we will be targeting around about £50 per kilowatt hour. Of course, this is reliant on having the economies of scale in place in order to realize it. But if we just think about the economics, the sustainability, and the ethics of the lithium-sulfur supply chain, I think we can quickly see that there's a very compelling opportunity. So let's think about possible sectors that can maximize the prospects of lithium-sulfur technologies. And as I mentioned, a vision of the LISTAR program is to try and identify early market opportunities that we believe will catalyze the overall industry. So we're looking for applications that can really value the lightweight nature, the high temperature window, the inherent safety, and the natural buoyancy of the lithium-sulfur cell. And so early market opportunities will perhaps be focused on heavy goods vehicles, large personal power packs, perhaps for military applications, marine and submarine applications, and perhaps of most interest in terms of early market applications, things that fly. Clearly, stuff that we need to get up in the air will have a huge benefit, both of the temperature window, but most importantly, in terms of the energy density per unit weight. The UK has obviously taken a global leadership position within the aviation sector. And as we look to decarbonise the aviation sector, there is a huge potential market opportunity, estimates of up to £4 trillion of the market for electric aviation by 2050. Aviation is, the UK PLC is a hub for aviation currently, and clearly as we move to electrified aviation, we want to retain the UK's leadership position. But I think we have to appreciate that the aviation sector is becoming increasingly diverse. So we're not just thinking about putting lithium-sulfur batteries onto auxiliary power units for transatlantic flights. There are many other applications that can perhaps earlier on in the development cycle leverage some of the unique benefits of lightweight and high temperature window that's provided by lithium-sulfur cells. For example, things that go up in satellites, things for vertical takeoff and landing, things for personal aviation, and things that will go in drones. And we project that with the improvements for gravimetric energy density, perhaps exceeding 600 or 700 watt hours per kilogram, there's a really exciting market opportunity in electric aviation. So we've set about trying to articulate a roadmap for the success of the lithium-sulfur battery technology platform. And this builds upon some thought leadership that was done by members of our consortium from Imperial College and from Oxis Energy back in 2018. And at the time, what they were able to do was articulate what the current state of the art was and project what improvements would be required in order to meet niche market applications and subsequently mass market applications. And the development cycle that we see it is that we need to improve cycle life, we need to increase temperature range, we want to improve the rate, and at that point we can target specific applications. The momentum provided by those targeted applications we envisage will then catalyze the whole industry to begin to make more improvements to durability, more improvements to the charge and discharge rate performance. And as a consequence, open up an increasingly diverse platform of applications. So briefly to conclude my part of the presentation before we move on to the Q&A, I wanted to focus on what we're doing within the LiSTAR program, the Faraday Institution's Lithium-sulfur Technology Accelerator. It's a program which has 7 partner universities led by UCL and 6 industrial partners. It's our vision to work harmoniously across industry and academia to try and develop this technology and extend battery performance beyond the limits of lithium-ion batteries. It's a program that is valued between about 8 and 10 million pounds, and we have a critical mass of close to 50 people who are working on the project across 4 different work packages. Those work packages are tackling some of those critical challenges that we previously discussed, trying to improve the cycle life, trying to engineer the materials to work around some of the fundamental limitations of technology. For example, the insulating nature of sulfur, trying to improve not only the gravimetric energy density, but also the volumetric energy density. And we're trying to adopt a relatively holistic approach where we have materials chemists designing very blue sky material solutions, right the way through to engineers who are developing battery management systems and components which are specifically targeted at the lithium-sulfur sector. We have 4 work packages in order to achieve this, focusing on cathode design, electrolyte development and fundamental electrochemistry, supporting modeling and simulation, and finally cell engineering. And because we feel that for the lithium-sulfur technology, there are so many intrinsically interconnected features, we're trying to tackle all of these things with a very holistic and multidisciplinary approach. And I think that this is quite nicely illustrated if we can consider just one component of the battery, the sulfur-carbon composite cathode that goes into the lithium-sulfur cell. If we were to do a quick mind map of all of the requirements of a lithium-sulfur cathode, we can see that we want to minimize electrolyte loading, maximize sulfur loading. We want it to be stable over many cycles. We want to enhance the electrical properties of the battery. But clearly, this is a very highly interconnected mind map. And so as part of our road mapping activity, what we try to do is to rationalize our design principles in order to best target all of those improvements that we want to achieve at the cell level. So, for example, if we think achieving a higher C-rate performance, we can directly translate this to improving electron and lithium-ion transport, which can in turn be translated to our materials scientists who are developing new conductive frameworks. Now, considering just high C-rate performance in isolation is in some ways interesting from a fundamental scientific perspective, but less useful when developing more technology. Because of the interconnection between the different cell features, if we just optimize one parameter, we run the risk of compromising other features of the overall cell performance. So when we consider improving the high C-rate performance, at the same time we're considering the impacts on the other performance metrics of the cell, and by having a rationalized design roadmap, we're able to consider all of these factors in concert. Just briefly to close before the Q&A, what are we aiming to do in the Lifestyle program? Well, we're working closely with industry, so we want to show translational aspects from the university lab into commercial reality. We want the opportunity to design bespoke systems from the ground up, so we are not necessarily going to be importing battery management systems, for example, directly from lithium-ion batteries. We identify opportunities to have ground-up bespoke materials and systems. We want to understand the interactions to benefit the whole cell, as I've already articulated, and across the consortium, we're aiming to improve the mass loading of active materials, we're aiming to improve the discharge rate, and we're aiming to improve the longevity of the cell. As I mentioned, our interactions with strategic industry partners are absolutely critical to the success of the program, and I wanted just to reflect upon the critical mass within UK industry of direct relevance to the lithium-sulfur technology, where we can see that across those industry partners, we've got a breadth of specializations in materials, in manufacturing, and in applications. And we're delighted to have such active participation and dialogue between industry and academia. And for anyone interested in finding out more about that, please do reach out to James Robinson and myself. We'd be delighted to discuss the program in more detail. It remains for me to thank you all again for attending today, to thank the KTN and the Faraday Institution for hosting this. And we will move on now to the Q&A section. As we do that, I'd also like to briefly introduce James Robinson. James is the project leader for the Faraday Institution Lifestyle project, and James is going to join Ian and I for the Q&A as we try and answer as many of your questions as possible. But as Ian said right at the beginning, if we don't manage to get to the end of all of your questions, do please feel free to reach out. You can see our contact details there on our website. We'd be very happy to take the discussions further beyond the scope of today's webinar. Thanks again. Over to you, Ian.
Thank you, Paul. That was really interesting, and it's good that you and James can stay around to answer questions. There are quite a lot of questions. I'm not sure we'll get through all of them. I'm going to try to group them where I can as well. So the first question, some of these have come in through the presentation, and you kind of hinted at answers as you went through. But the question is, what's the impact of lithium-sulfur going to be on electric vehicles? What does it mean in terms of performance, range, and that sort of thing? And tied up closely with that is of the different applications, what do you think is going to be the first applications for lithium-sulfur batteries, and where do EVs sit within that? So over to you.
Sure. So I'll perhaps just kick things off, and James, do feel free to jump in with any contributions. So as I mentioned, the lithium-sulfur battery technology is clearly less mature than lithium-ion batteries, and some of its unique attributes don't immediately play into the passenger vehicle sector. If you look at lithium-ion batteries, both for consumer electronics and for passenger EV applications, they've often been very highly optimized to deliver volumetric energy density. And if you look at a good lithium-ion battery, you're probably looking at somewhere in excess of 600 or 700 watt hours per litre, but only 150 to 250 watt hours per kilogram. So in order to be successful in early market applications, the lithium-sulfur technology is addressing things that can benefit from being intrinsically lightweight. And at the outset, that's probably not passenger electric vehicles. That's probably things that fly, that can obviously take advantage of its lightweight nature, but also its high thermal stability. There might be things that need to be carried around, so things like on-person power, which might be important for military applications, for example, and also for heavy goods vehicles and possibly some bus applications where lithium-ion battery weight in the size of packs required to service that application become somewhat rate limiting in terms of their deployment. So I think that potentially in the longer term, there might be a role within passenger EV. Certainly in the sort of near to medium term, the volumetric energy density competitiveness of lithium sulfur cells will probably see it commercialized elsewhere first.
Just to follow up on that, Paul, I think we've seen the early sort of steps of commercialization around lithium sulfur in the heavy goods vehicles, as you've mentioned. So Oxis Energy have signed a deal to start producing lithium sulfur powered electric buses, and that's going to be from about 2023. We'll start seeing those. So that's a deal between Oxis and Mercedes, and then the kind of the early rollouts will likely be in drones and sort of high altitude pseudo satellites, before we then start moving towards electric aircraft, which might carry people.
Good. I've got another question here, and it might be one that you want to go and scratch your back and back of the packet calculations on. It's how much lithium do you need per kilowatt hour in a lithium sulfur battery? And I guess as a point of reference, you've got to compare that with how much lithium goes into a kilowatt hour of reasonably quality standard lithium-ion batteries. So unless you nod and you know that off the top of your head, we'll come back to that one when you've had it.
I think that is one that we'll go and do our calculations on. But what I would say is that clearly with the lithium sulfur cell, we're looking at a metallic lithium anode. So with that metallic lithium anode, if you compare that to the lithium host within a lithium-ion battery being, for example, lithium cobalt oxide as the sort of primary lithium source, we're not carting around all that extra cobalt, all that extra oxygen with it. So intrinsically, there is scope for significant reduction in terms of the materials that go into the cell, but that relies on getting the materials engineering and the cell engineering right, so we don't have to operate with an enormous excess of lithium within the cell. So I mentioned in one of the earlier slides that there are some very ambitious targets that look at the 5 5s in terms of the excess of electrolyte and also in terms of the excess of lithium that's required in a competitive cell technology. On paper, the lithium sulfur battery should give us a remarkable advantage in terms of the gravimetric energy density because that lithium metal is so much more energy dense per unit weight. In practice, we have to ensure that that is translated to a viable product by minimizing the excess of lithium that we use.
Okay. Got a question from Adam Vaughan. How many years off are we from seeing lithium sulfur in products? So we've talked about the plane. You said 2023 was Mercedes in trucks. Do you think that's likely to be the first lithium sulfur in products, or how optimistic do you think 2023 is?
So I think in terms of the manufacturing we're seeing, the plans are really there at the moment to start opening up factories across the world at the moment. So This factory in Brazil is planned for 2023, but actually there'll be a factory opened up in the UK designed to build cathodes and electrolytes, which will be opening up towards the end of next year, and then scaling up capacity as demand for lithium sulfur increases. So I think in terms of initial rollout, we're actually in a really good place. We've kind of managed to hit the early stage of the rollout, and the developments that occur during LiSTAR can sort of go in concert with the initial application development, and then hopefully feed in as the technology matures.
Good. Got a question: how do degradation effects differ between lithium-ion and lithium-sulfur? Do they degrade in the same way?
I mean, the short answer is no. They don't degrade in the same way. We're using very different electrodes in the lithium-sulfur system, and because of that phase transition from solid electrodes to sort of liquid active materials during the charge and discharge process, there are some quite different degradation processes that happen, and again, that provides us with some challenges in the fundamental understanding of that, but also, given the insight that we are gaining from our fundamental investigations of electrochemistry and material science, it provides us with some really exciting opportunities to engineer designer materials that can be much more degradation tolerant. One of the major challenges in terms of lithium-sulfur durability is what's known as the polysulfide shuttle effect, and also that's associated with possible inventory loss. As we get crossover of the active materials from one side of the cell to the other, they can become effectively lost capacity within the cell. So coming up with smart solutions on how to effectively trap the active materials whilst not compromising the performance of the battery is one of the routes that we're pursuing within the program.
I've got a question. I guess this was probably for James. If you're not currently a member of the consortium, how can you be involved in the project?
I think the easiest thing to do is just to get in touch with either Paul or myself. We're always sort of quite keen to hear from new people and to hear new ideas. So please do get in touch if you can do. And
as an alternative, contact me and we can talk about the totality of Faraday Institution program and how we could best work together. Next, how important is the BMS for lithium-sulfur?
Short answer is, I think it's really important because there are some fundamental differences in the charge-discharge characteristics of a lithium-ion battery compared to a lithium-sulfur battery. One that has been talked about quite extensively is that the lithium-sulfur battery goes through local minima and maxima in its internal resistance, and therefore being able to intelligently balance a bank of lithium-sulfur cells is the dip to what you'd be used to if you were dealing with lithium-ion batteries. And that is exactly why within the LiSTAR program, we are developing the materials and the cells and the operational and control strategies in concert.
Looking down the list. So when we got lithium-sulfur cell, lithium anodes is one of the things that we're looking for. So how close do you think we are to solving the lithium anode, metal anode problems?
Good question, and I could probably wax lyrical for about an hour and a half about that. I'll try and keep it brief. I think that for a range of next generation battery chemistries, employing alkaline metal electrodes is often seen as the kind of holy grail. I think that when you look at the solid state battery community in particular, it's a lot more difficult than people initially thought. I think that if we take solid state batteries as an example, it was always expected that below critical current densities, the solid electrolyte would block the penetration of lithium dendrites during charge and discharge. And obviously over the past 10 or 15 years, that's been shown not always to be the case. So these are inherently unstable or maybe metastable materials, and engineering and designing solutions to make them more stable over long cycle lives is challenging. But what I do think that we've seen within the lithium-sulfur development is some very interesting proposals, particularly perhaps around electrolyte additives that can decompose into providing a very stable solid electrolyte interface at the anode, as well as a range of different solutions on making protected lithium metal anodes that I think are really exciting to pursue. And back to that comment about solid state batteries, obviously the SolBat program, which is another one of the Faraday Institution's research, large research programs that's been going now for a bit more than 2 years, have made great strides towards both making solid electrolytes, but also making protected metal anodes. And, you know, within the Faraday Institution ecosystem, it's great to be able to have an exchange of ideas between, for example, the SolBat program and the Lifestyle program, because I think it makes us, you know, greater than the sum of our parts. It means that we can really directly import their state-of-the-art innovations in protected metal anodes into our lithium-sulfur ecosystem.
James, anything to add?
No, I just think alongside that, so the SolBat program and Lifestyle are actually quite closely aligned. So I think, as Paul mentioned, the ability to kind of maximize the research that's ongoing in the Faraday Institution is a real addition to the research program.
A straightforward question, hopefully. What voltage is a 0% state of charge equate to, roughly? I.e., do they discharge all the way down to zero?
You can discharge them all the way down to zero, yeah. So, I mean, if you look at a lithium-ion battery, you're probably looking at shipping at about 30% state of charge, and that's because of principally because of some of the reactions between the active materials and the current collectors at very low voltages. That's not a problem that we have in lithium-sulfur batteries. So they can be shipped at 0% state of charge at 0 volts. You can short circuit the tabs if you want, and that makes it a lot easier to ship because you're no longer shipping according to the active battery shipping protocols. These can be shipped, I believe, as commodity chemicals.
I think the one thing to add there is that translates actually to being able to ship them by aviation. So effectively, you have a bag of chemicals rather than sort of a live battery, which has a huge impact in terms of cost and in terms of ease of shipping.
Good. Next, can you quantify comments about volumetric energy density? How much bigger are they than lithium-ion?
So I think that we can talk about sort of current state of the art, and we can talk about it. Let's start with targets. What we would like to do is to get a cell that has in excess of 500 gram and about 500 or in excess of 500 watt-hours per litre. If you look at current generations of lithium-ion cell, we are probably at about 200 watt-hours per kilogram and 700 watt-hours per litre. So I think the lithium-sulfur is naturally going to outperform the gravimetric and underperform the volumetric, but we're hopeful that we're targeting 500 to 600 watt-hours per litre and 500 to 600 watt-hours per kilogram.
In a historical sense, the volumetric and gravimetric energy density have kind of coupled one for one. So as you add 50 watt-hours per kilo, you tend to add 50 watt-hours per litre to the overall target.
And I guess related to the targets, I think we had a target of 500 cycles. Is that going to be enough, especially when we're looking at things like aerospace applications?
I mean, clearly with cycle life, more is better in almost every application that you can possibly conceive of. But 500, I think, is adequate in order to target some early market applications. And actually, for really niche applications, and I'm thinking maybe particularly about the defence sector here, you might get away with substantially less than that, because some of these batteries, operate for short periods of time in very extreme environments and are then ultimately disposed. So, of course, more is better. I think 500 would open the doors to quite a number of applications. I think that if you look to electric vehicles, there is a sort of general gut feeling that people want to get to 1,000 cycles down to 80% of initial capacity. Not even all lithium-ion batteries meet that target as it stands. So, yeah, I mean, I think that 1,000 cycles would be nice. I think that 500 cycles is adequate. And probably the key message is that it is so application dependent. Your iPhone battery or your mobile phone battery probably doesn't need 1,000 cycles. It probably needs sort of 500-700, couple of years worth of use. By contrast, something that goes into a grid scale application that might be there for 20 years might need 10,000 cycles. So there is such a diverse need for energy storage that I think you can really begin to cherry pick what your critical metric is, whether it's cycle life, cost, power, energy density, safety, and already you can conceive of ways in which next generation batteries can be competitive or exceed current generations of lithium-ion batteries. And I think that's how we're going to get a foothold in the market, is by working out which of those niches we can tackle first.
Okay, you kind of hinted at this one, but the questions just come in a bit more detail, and it's can you just go into don't give us the full detail, but why can't lithium-ion batteries be shipped to zero charge, and therefore why can lithium-sulfur? What's the key difference?
Well, one challenge with lithium-ion batteries is that if you discharge them to 0 volts, you can get a reaction between the electrode and the current collectors, and that doesn't happen in lithium-sulfur batteries because of the different materials and current collectors involved.
Good. And this might have to be the last question. Can the UK be a manufacturing hub for lithium-sulfur?
I'll let James take this one, but my response is an obvious one, which is I think absolutely yes.
I'd echo your thoughts there, Paul. I think the UK is in a really strong position for lithium-sulfur. It has a sort of an existing ecosystem of really high quality materials producers. It has a leading group of academics who are sort of driving the research forward, and then it also happens to have an existing lithium-sulfur infrastructure through Oxis Energy, which are probably the world's leading lithium-sulfur manufacturers at the moment. So I think the opportunity for the UK to harness that at this early stage and really become the world leader in lithium-sulfur is there. And I think with the backing of the Faraday Institute and the developments that sit along the LISTAR program, we're in a really good situation to maximise that.
Thank you, James. We're trying to work out if we've got time for one more quick one. I think probably not. There are one or two extra questions, but they're slightly more involved. So the people that have got questions still unanswered, we'll get back to you on those after the meeting. But I think that there are no 2-minute questions left. So I think it's probably good that we wrap up at that point. And all I've really got to say is a thank you to everyone for the contributions, and thank you for attending. We've had well in excess of 100 people on the webinar today. And we'd really like this and these sorts of events to be a catalyst for deeper engagement with us at Faraday Institution headquarters and the researchers on the team. So please stay in touch. There are many more ways to find out more and engage further. Most of the information presented today is available on the Faraday Insight documents. These Insight documents are really concise briefings that give basic information about the different chemistries and different aspects of batteries. You can access them all on the links, and these slides will be sent out to you. There are different ways that we can work with Faraday Institution. We have a scheme of industrial fellowships. You can find out more about those, again, by following the link. And that's when people actually come to work closely with the researchers to either contribute towards the research or to give an industrial perspective to that research, or maybe just build links with academics in the UK. You can request one-to-one meetings via Meeting Mojo with either myself or Paul or James. We're welcoming approaches really from anyone that wants to work with us and get involved in the projects that or know more. We're trying to get information about batteries and latest technologies out to UK industry and help UK industry develop things on the next stage through the academic research and link with other people and building projects that can deliver in partnership. And finally, we've got 2 public consultations going on with BSI, the British Standards Institute. The first one is on battery electric vehicles and how do you design them for safe and environmental use. And it's aimed as a guide. The second one is about batteries and cell design, particularly again for electric vehicles. Health and safety support in doing that, and the intention is that to be a code of practice. They're in reasonably early stages of development, but we're looking for consultation on those draft documents to make them as strong as possible. But finally, we're interested in people joining Faraday Institution's challenges and other events in the future. So this is the final of 3 Faraday Battery Challenge webinars. I hope if you attended more than one, you found them all engaging and you found them all useful. The first one was about growing a battery business across sectors. The second one was last week, and that was an update on the Battery Industrialisation Centre and how to work closely with them. And then this one, looking at maybe future battery technologies, things that are close to market on lithium-sulfur. We're looking at what we can do to do another set of these webinars in the autumn, so keep a lookout in the autumn for the content of those. And all that really remains to me is thanks to everyone for attending, and thank you very much to Paul and James for taking time to answer questions and to educate us all. Thank you.
Pleasure. Thanks so much for joining today.
Thanks, Ian. Cheers.